Okay, welcome everyone. Welcome to our very first part one of the Biocontrol Research Masterclass series. Today we're really going to focus on getting to know everyone in the room. So really take the time to introduce yourself, and I'd really be keen if you could actually also tell us what you're working on or what you have been working on. We'll have a little bit of an informal poll soon to sort of get a bit more information about that, but it would be nice if you could start sharing your research, what you're interested in the actual chat, because that'll create a bit of conversation as well. And you may even meet somebody in the chat that's working on the same thing, which is part of what we want to achieve today, is a little bit of networking as well. And we'll definitely focus on that throughout the 3 sessions. So we're going to be looking at efficacy, trial design, introductions, and some other goodies in the bag, I guess, that Roma has in store for us. My name's Alison Watson. Putra is also joining me as project assistant on this project to help out. And of course, we have Roma as well, who will be leading the session. Just before I move to the next slide, I just want to give a big thanks to Valent Biosciences and Semio-chemicals for actually supporting this whole series. It's wonderful to have you on board, and it's a really important part of building capability and capacity in the region. So if we move to the next slide, I'm just going to remind everyone that today the best way to actually interact is through the chat. So just put all your questions, share all your comments and resources in the chat. Let's have a really big conversation. You don't need to use the Q&A because I've actually taken that off, because it's just easier that everyone can see what everyone's saying. You can raise your hand if you'd like to chat, and we will leave some time at the end as well for a bit of a discussion. So if you want to tell us what you're doing, by all means put your hand up, and we'd be keen to hear that from you directly. If you can rename yourself if your name isn't in there, that would be great as well. So just quickly make sure you introduce yourself in the chat. Please put what organisation you're from, also what research interest you're working on, and please use it. Go for it. I'd like to see lots of information in that chat box. Moving on to the next slide, I just want to really reiterate that this is part 1 of a 3-part series, so please join us on the 9th of June and the 22nd of June. Between each session, we're actually going to send out a questionnaire to you, so we want to really gather some more information, and then we'll feed that back into session 2, for example, so that we can actually really have a really interactive series. Now, what we're going to do is, before we move on to the next slide, I'm just going to launch a poll. We're going to have a little bit of an idea of who's in the room, and then we'll move on to the main event. So I'm going to launch poll 1. Let me see if I can do this all okay. It should be coming up on your screen right now. And what we want to do here is just get to know what you're working on, particularly the main thing that you're working on most recently, or maybe where you've got most expertise. But what agents, semio-chemicals or biopesticides are you working on? So you've got a choice there, and hopefully people can see that. I'm not getting anyone answering it, so I'm not sure it's coming. Oh, yes, it is coming up. There we go. We're just a bit slow there. Now we're getting some participation. I was a bit worried it wasn't working.
It is a big poll, so it's just going to take a little bit of time for everybody to work through it. But
exactly.
Yeah, the more people who can answer this, the better. And I think we know that some people on the phone may have trouble.
Yeah.
So we will. This poll will be available as again to complete.
Yeah. We'll put the questions in the Survey Monkey. And also, if you can't answer the poll because you're on a telephone and it's not working, you could just put a quick answer in the chat too, around what you're working on. Mostly, we've got a bit of a race at the moment. The clear leader is the bacteria, fungi, microbials, I have to say, by quite a lot. It's winning. What type of biotic factor is your biopesticide for? So clearly insects, 84% at the moment. How long have you been working on this biopesticide product? Now, some of you might be working on various products, but just sort of give us a bit of maybe choose your most recent one, or the one that you've been working mostly on, or average it out, I guess. And what is the main reason you decided to work on your product or project? We were just interested here to know sort of what's driving people's choices or their research. So that's interesting. And how did you obtain information of farmers or market needs of biopesticide? Try and pick two only. I know it's tempting to pick them all because you get information from everyone, and it may even be tempting to just pick farmers, which is great, but be honest if you can and pick the two that you normally get most of your information from. So there's lots of questions there, and actually we've got a lot of people that have answered them. So we're actually 63% participation, so that's actually fantastic. I'm going to see if we can just get up to sort of over 65%. And I see Lee Chun Yin has raised your hand. I'll come back to you and find out what the problem is, or if you want to say something very soon. So if you just are patient.
And we've still got people joining as well. So for the people joining, we're running a poll. If you've got time, you can quickly fill it in.
Nice to see Chin from Semio-chemicals Vietnam. Hi. Right. I think I'm going to launch this now with 69% participation. Oh, we just got some instant, as I said that, 72%. So I think I'm going to end the poll. Excellent. And I'm even 74. Wow, that's actually really good. And I'm going to share the results, and let's have a look who's in the room and what people are saying. You should be able to see that. Can you see that, Roma?
I can. Yeah, that's really interesting. So that first trend of the majority of people working on microbials, but I'm really interested to see how many people are now working on semio-chemicals and botanicals, and maybe where people have put others, we can explore that later in the session. So the people who've marked other, what would be really great is if you can put that into the chat, what the other is, so that we can see that and share that. But yeah, it's sort of what I expect. The majority of people are working on microbials, so really good. Then if we could look at question 2, the type of biotic factor is your biopesticide. So again, it looks like most of the people participating today are interested in insects and see that as the biggest problem, pathogens. And I'm not surprised fewer people working on weeds, just because it's so hard to find biologicals that work on weeds. So that really sort of makes sense. And it's working on that. Well done. It's a very challenging area of work. I'd say insects are the biggest problem. But then looking at how long you've been working. Oh, some of you have got really long experience at 6 to 10 years. So this is yes, you've spent a large part of your career working on them. But really interesting to see there's a lot of new people come into the field. About sort of 30% of the people are new into the field. And the 1 to 2 years. And I'm really interested that there's the 3 to 5 years is the biggest group, because I suspect that's to do with funding cycles, and that's something that we're going to talk about today. And it'd be really interesting at the end of the session to come back and say, is the 3 to 5 years because of funding cycles? And then some people have 10 years. Excellent, really good. So then the main reason to work on your project. Now this I think is very interesting.
It is.
Yeah. So some of that is to do with funding. Really interesting. Oh, quite a few of you must be doing PhDs because it's continuing on from a previous degree. Collaboration with industry. Now I'm really interested to see so a high number of people have collaboration with colleagues and industry as well. And then those of you who've answered other, again, really, could you put into the chat what is the main reasons why you decided to work on your project? Because there's a lot of you who've marked others, so we've missed a question there. It'd be really good to understand that question we've missed is, and we can put it into the poll when we rerun it. That's really good. And how do you obtain information of the farmer's needs? Now this is really interesting. So a lot of you obtain the information from universities, some of you private sector, some of you from the journals, and some from the government extension workers. And then I'm really impressed to see that 40% are getting your information from the farmers. That's really quite interesting. And it shows you've got good contact with the end users and what the farmers want. Very interesting results from that. I think we can learn a lot from that. And please, put into the chat any comments you have, because you've all now seen the results of the survey and shared it. And so what do you think about that? And do you think that's what perhaps needs to be changed, and what we can do to share more of this work?
Excellent. That's really interesting, and we'll definitely share those results with you as well, but you'll have another chance to fill out some answers to questions as well, so that we can bring that back and show you for next session. So that sort of ends that sort of introduction, but I just want to move on to the next slide, and just I think that's the introduction to you, Roma, and welcome back. And look, we're very pleased to have you on board. We've been getting together every week for the last couple of weeks, so it's been a pretty intensive learning time for me. I've learned a lot, and I'm really looking forward to today's session as well. So welcome, and the stage is yours.
Well, thank you very much, Alison, and thank you for inviting me to take part in this today, because I think it's a really important part when you've got a new technology like biological plant protection, that we share our experience as much as possible, because that way we can all move forward much faster by collaborating. So just to set some of the context of what we're talking about in these technologies, what we saw back in the 50s and 60s, and probably before many of us were born, was there was a real need to increase food production in the world. And there's a tremendous invention in new plant varieties, which are with high yielding varieties, with also having high input fertilizers and high input pesticides. And that allowed us to do a really good job of feeding a lot of people. And the landscape that you can see in this picture is an intensely beautiful landscape. But what we realize, it's a highly managed landscape. And as humans, we've changed significantly the landscape that we're working in. And somehow, since the sort of 50s and 60s, there's a balance been changed. And we realize that, yes, we did a good job of feeding the world. But then we also changed the environment, and we started to realize that there was some harm happening as a result of what we're doing. And increasingly we think, well, that's unacceptable harm, and we want to do something different. And that's where we are today, is sort of saying, can we produce food really well, but reduce the unacceptable harm that we're causing to environments? And that's where biocontrol comes in. It's the technologies that can support that approach. And the other thing we realize that, and I find this startling, in my lifetime, the world's population has doubled. The amount of farmable land is not being increasing. So what's happening is the amount of farmable land per person has been decreasing, which means we have to be better at producing a higher yield from all the farmed land. And that's the tension. We're saying, how do we do that without causing unacceptable harm to the wider environment and to the humans who interact with that land? And then the way we farm is difficult. So as ecologists and biologists, we know about ecosystems. We know the complexity that is ecosystems. And we know that the more complex an ecosystem, the more stable it is, which means the flip side is if you have a monoculture, which is what we're doing when we're growing food, is they're going to be inherently unstable. And so we start to ask ourselves and say, how do we manage that crop, which is inherently an unstable ecosystem, and make it a more stable ecosystem? And this is, I think, where biocontrol has a really big role to play. And as we'll talk through the sessions, hopefully you'll start to understand what I'm saying and why I think we can create a more complex ecosystem without necessarily changing that we're working in a monoculture. And as we move forward, the way in which we may be causing unacceptable harm has actually been captured by the United Nations in their Sustainable Development Goals. And what they're saying is, yes, we want to feed people, but we don't want to cause the same harm. We need to think about the life on the land. We need to think about how we're growing food, the ways in which we're growing food. And then we see this also encapsulated in places like the European Union, where they have developed what's called a farm to fork strategy. And they're aiming to say, well, we want to feed people and to grow food, but it should have a neutral or positive environmental effect. How can we mitigate climate change? How can we reduce the loss of biodiversity? And again, there's increasing thoughts that biocontrol is something that can really contribute to this, where we're causing less harm. That's not to say that biocontrol can't cause harm. It's saying that that a lot of what's coming forward is being developed in a way that it won't cause harm. And then we think about, so we've got a problem with we've got less farmable land, we've got this unstable ecosystem, and we're trying to farm better. But part of that system we've got at the moment is we're still losing 30 or 40% of the crops before harvest and about 10% after harvest, which says, is the crop protection model that we've got the right model? Because we're still losing so much to pests and diseases. So we need best practice. And where I'm coming from, I think these biological technologies are increasing the mainstay of sustainable crop protections and best practice. And perhaps I'm a little bit backed up with that in the sense that the markets for these technologies are growing. They're growing really fast. We're looking at compound annual growth rate that's estimated, some say over 20%, some people are more modest and saying 15%. Either way, that's very high, and compare that to a chemical, which is at 3 to 5%. You can see that biologicals are growing really fast. They had a really slow start. They represented a relatively small part of the crop protection market, but we're really seeing that we're beginning to move out of what I'd say that the lag phase, and we're moving on to that sort of log phase, where I think we're starting to see really rapid increase. And there's a lot of interest in these technologies, and there's a lot of technologies coming forward, and we can see the farmer acceptance of these technologies is improving. And before we sort of go forward and think, oh, this is impossible, you know, what I'm saying is not really viable. So we take the example of Brazil, you know, in really big country, and we perhaps have a picture that in Brazil there's a lot of pesticide use and perhaps a lot of harm. But is that entirely true? So in Brazil, there's 77.4 million hectares of crop production, and what we now know is that 10 million of that is using biocontrol. And then we look at the satisfaction that farmers have. 98% of the farmers who use biocontrol products in the 2017-2018 crop season would use the products again. So what we can see is adaptation is changing. The farmer acceptance of these technologies is changing. So we're really, I think, at the beginning of, it's not quite a revolution, but it's a really fast evolution to different approaches to crop protection. And for me, this crop protection is sort of, it's about biology. It's thinking as biologists, and it's thinking as ecologists, and how do we grow food in a way that's causing less unacceptable harm. So what's driving the market? Who wants the products? Why? What do the products offer? So we think about the reasons for the uptake of these technologies, and there are multiple reasons. The first one I got there is efficacy, is because these products actually work. Often I ask these questions to students, and the students forget to say that the products actually work. So let's hold that in mind, that these biocontrol products do work. We'll explore a little bit about what we think that means when we say that they're working as I go through the presentation. And one of the things we can see is yield and quality improvement. So it's not just that you yield your pest, but it's also you're doing things to improve the quality of the produce. They're useful because you can have quite a good degree of host specificity.
Oh, I think we might be stuck with the connection. I'm just going to give Roma a couple minutes.
Entry or a harvest interval.
Sorry, Roma, we did just miss quite a bit of that, just for about maybe 20 seconds.
Okay, I'll go back through. So, okay. So the reasons why for the uptake of bioprotection in agriculture is, yes, they work, so efficacy is good. We can use them in IPM programs. They're really useful for resistance management and residue management. Growers find them useful because a lot of the products don't have re-entry intervals, and they don't have harvest intervals, which means that the farmers can protect the crop right up to the last minute before they're harvesting. And they're also sort of useful in organic production. So what are these biocontrol agents? So we have 4 categories. We've got invertebrates, microbials, natural substances, and semio-chemicals. Around the world, there's different definitions, but broadly, these are the definitions. So you'll also see them called all sorts of different names: bioprotectants, biological control solutions, biorationals. We're more or less talking about the same thing. So talking a little bit about predators and parasites, these are sort of macroorganisms which are either eating other insects, laying their eggs into other insects, or burrowing into them and killing them. Then something to think about biocontrol is we sometimes forget, and this is perhaps something you might have touched on in your research, is that there's a lot going on in a monoculture, in a crop field, without us doing anything. So if we think about it, if there was no natural control going on, if you had one cabbage aphid that was just allowed to breed, in 1 year you'd have 250 million tons of offspring. Now, clearly, when you walk into field, we're not seeing that. So biocontrol is operating all the time. And that's a little bit about what we're trying to do, is to understand what's going on naturally in these cropped environments. And I think if we think about sort of research, I think there's space to have some good research to understand what these mechanisms are and how big an influence these mechanisms are having in a crop system that we perhaps have missed, or we're perhaps not looking after, or we're perhaps damaging. And a good example of this is through the Fall Armyworm project. You probably know how big a problem Fall Armyworms, Spodoptera frugiperda, is, and the damage that it's potentially causing. But there's some interesting work that's coming out of the global action for Fall Armyworm, is that they've found that using natural enemies, that there is a significant reduction in the Fall Armyworm because of good practice to manage and encourage the natural enemies that are there. So before we sort of think about interventions that we can put into the crop, so we should think in research about, let's understand what that baseline is, what's there, what's already operating, and not forget that although this is a monoculture, there is a lot of biology, ecology going on that we might not be looking at or understanding. But the main way a lot of these macroorganisms are used is intentionally released, what's called augmentative control, and we can see products such as these being used, originally developed in greenhouses, but we're seeing more increasingly these are moving into the open field situations. And then thinking a little bit more about microorganisms, and this seems to be what the majority of you are working on. So for microorganisms, we've got a lot of different species that are being used. When we're thinking about microorganism species, we need to think as researchers, we need to think about strains, because as biologists and ecologists, again, what we know is that one strain can be very different from another strain, and we need to be thoughtful and think about that. But I also will come back to this again. In terms of doing research, do we always need to work with a new strain? Could we do research on an existing strain and find out more about it? So just think about that. So with the kind of microorganisms we have got fungi and bacteria that are active against fungi and bacteria. Very few viruses coming through against plant diseases. But again, that's an area of research where I've started to see 1 or 2 papers coming through. Then we have microbial insecticides. So we've got fungi against insects, we've got bacteria against insects, and we've got viruses against insects. And what's critical about these is understanding how they get into the insect and what the interaction is. So this part about the mode of action, how these work, and how the research that we should get involved in there is something we'll cover in the next session. But most of what we see today is the way that microorganisms are used is in a very binary way. We have an insect, we have the microorganism, and we put one against the other, and we hope that something dies. So then moving on and thinking about our botanicals. Again, a lot of you are working on botanicals, and I will explore in the sessions, and it'd be great if you can put into the chat as to what botanicals you're working on. So these are substances extracted from plants, and then they're used and sprayed back from plants. And again, when we pick up on thinking about the mode of action, if we think about it comes from plants, it's no surprise when we put it back onto the plants that it might be inducing some of the similar things that it does in the plant. And again, exploring what that looks like. So botanicals, they're compounds, they're multiple molecules, they can have physical mode of action, they can have direct kill effects. It's a really very complex group of substances. And then lastly, we've got semio-chemicals, and this is something that is emitted by one organism and it affects behavior of another organism. So you're not having direct kill. Best known of these are the straight chain lepidopteran pheromones, and most of those are mating disruption. So we can see that where we can see that the pheromone is absorbed onto something like PVC. And in this example, you can see this is wrapped around the stalks of rice and put out across the field. It then has a slow release of pheromone, which stops, which then confuses the male and you don't get mating. And you've got something like a puffer system, the same idea, it's a slow release system. So semio-chemicals can be used for mating disruption, they can be used in lure and kill and in mass trapping. So just to summarize, that was a quick run through of what the technologies are, just so that we all understand, because sometimes we're in silos in our research, aren't we? And you're working on a microorganism and you're not realize that somebody could be working on a botanical against the same organism, and perhaps you can collaborate because you have the same aims from what you're doing. So these technologies can be used in a range of different ways, but the main way we see them being used in agriculture is the inundative or inoculation, and most of the time when we're developing something in our research is we're thinking in that way. And then we use these technologies in the field in integrated pest management, where the farmers are following a lot of other practices, agronomic, monitoring, forecasting, physical intervention, and then coming with a biological intervention, and if you needed, the chemical. So again, as researchers, we need to think about what we're developing and thinking about where it's going to be used. And just, I kind of like this to remind myself sometimes, we often think we're doing something new and we're inventing. And we think integrated pest management or integrated vector management is something new. Actually, it's been in place since the 1950s. So it's been in place a long time. And perhaps only now are we beginning to have all the tools and understanding to understand the underlying principles of what's going on in a field, in a monoculture, to start to use integrated pest management in a good way and have good practice. So that's by way of my kind of introduction, and that's by way of sort of just getting us all into the same place about what technologies we're working with and what we're thinking about. And I just want to take a little bit of a pause to see if anyone's raised any particular questions so far. Alison, has anything come through?
No, but we are very busy in the chat, so that's great. And it's more just a big, I guess, just to repeat some of those questions. I mean, one of those questions Roma just asked was, look, if you are working on botanicals or if you're working on any of those, feel free to put that in the chat so that we can see what you're working on. We've already had quite a lot of discussion, and I've been very busy making contacts with people as well. But the more that you put in and share, the more that you'll get out of this session as well, because you'll see what other people are working on, and we'll build that network as we go.
Yeah, because it'd be really great to have an outcome from today is that you find a colleague who's working in a similar field with you, and that you can share your expertise and share your knowledge together. So what I'm going to do next is start to think a little bit about what's happening in research and development. So what we know about working in this field is we've got a wide range of technologies. We've spoken today that we've got people who are working with microorganisms, botanicals and semio-chemicals, and I expect some of you are working with macroorganisms as well. So as soon as we start working this technology, what we know about this is it's really knowledge intensive. It's really complicated technology, and it's really quite new. And like I said, for the microorganisms, it's not just, there's some things you can generalize about species. So you can say Beauveria bassiana microorganism is an insect pathogen, but is Beauveria bassiana strain A the same as strain X? do they behave in the same way? They probably don't, because what we're now dealing with is quite an intimate relationship between the host and the biocontrol agent that you're using. We're always, you know, in that evolutionary race for who's going to win that evolutionary race, which makes it really complex about how the insect population responds and how we work with the technologies. And we sometimes think, oh, botanicals, they're kind of like chemicals. Far from it. They're really quite complicated, and the modes of action they have. So once we're starting to work in research and development, it's really complex. We can be sitting in our world working on something and not knowing the context in which we're working, not knowing what's happening. But when we're moving in research and development, because it's so complex, it also actually takes a long time and is expensive. And this is some of the reason why it's taken so long for some of these technologies to come forward and for to get into the marketplace, is because of the amount of research that's needed to move the technologies forward. So there's a lot of things that are now in the market. I know researchers were working on when I started my career over 35 years ago. But you think, well, actually, we can't take that long. We need to find ways to be much faster at doing this because it takes too long. And that's what I sort of want to explore is how can we do this really well, but do this a little bit faster? How can we be more targeted in what we're doing? So in the poll, we asked questions about how long you've been working on it. And I think we saw that the majority of people have been working on it 3 to 5 years. And I have a suspicion, and you can put in the chat to say whether I'm right, or put up little thumbs up if I'm right, or thumbs down if I'm wrong. I think a lot of people have been working that long is because that's what the research funding cycles are on. And that many of you would like to keep working in this field, but research money isn't coming in, you're have to move on from your university, and you're not able to stay in your career. So what I see happening for most people who are working in research is they follow what I call a linear product development pathway. So you start your research, and the first thing you'll go and do is think, okay, can I go and what do I start working on? Can I go and find my isolate? If it's a microorganism, what a botanical material am I going to be working for? And then the first thing you're thinking is, okay, what does this do? What does it kill? How good is it? Usually you have an idea what you expect it to do, and so what you're screening the substance against in a petri dish screen is you've got an idea of the insect you should be targeting or the disease you're targeting, or you'll have a range of diseases there. And then you found something that shows activity and think, okay, I need to do a small pot test to check that out. And then perhaps got some questions of sort of saying, if it's a microorganism, you think, okay, I've got enough to make a small pot test. How do I make a little more so I could do a bigger experiment? And that actually is quite hard to do if you're working in a lab. And then you've got some work and saying, okay, so I found something that works really well. I tested this number of strains or isolates or botanical compositions. And then you try and get to small scale tests. And all of that has taken about 4.5 years. And then often what happens is there's no money, you finished your master's, you finished your PhD, and then you move on. And a lot of times that lovely research just sits in a lab, sits in a publication, and is not going any further and is not being developed. But if we think about how a commercial company might develop a new product, it's very, very different. And what I'd like to sort of think about is saying, can we take some of these principles and move them into our research? So the way in which a commercial company will develop something is much more of a matrix pattern. They do lots of different things at once. And what's interesting with them is the first thing they ask is the market assessment. And this is what I wanted to explore, is when you start a piece of research, and if we're working in biocontrol, most of the research in biocontrol is for applied. So therefore, if it's going to be applied, it means you expect it to be something that's useful to the farmer. When you started that research project, did you really look and understand what the farmer's problems were? What solutions did the farmers need? And that's something I often see on research projects, is not thinking about what I'd call the market, is does the farmer need this? Am I doing research? I'm working in an applied area. I'm working on something. Am I working on something that is a solution that the farmer's going to need at the end of the day? Now, there's space for research which is less directed than that. I absolutely know that. But often what I'll see is somebody saying, oh, I've got this really great isolate. And I'm saying, well, okay, what does that kill? And then the researchers are going, oh, I don't know. And as they're saying, well, okay, you're going to screen it against some targets. What diseases or what insects are you going to screen it against? And there's not a really good understanding of the problems that the farmers have. And I was really interested in the poll that we did, that in fact that a lot of you are driven by what the farmer's problem is, but not all of you were. And there may be good reasons why they are not driven by that. But it's sort of thinking, if you're trying to develop something that's a solution to farmers, the first thing you need to go out and do is find out what the problems the farmers have. And that's something that commercial work always does right at the beginning. And then they sort of say, okay, how can I, if that's the problem, how can I do the research and how can I streamline this process to get to that marketplace as quickly as possible? So the first step that they'll have is what I call active substance acquisition. Now, as researchers, what we'll tend to do is we'll go out and look for a new strain, a new isolate. And oftentimes, if you're doing a PhD, your supervisor will have said, right, the first thing I want you to do is go and find a new isolate. Now, I'll raise a question there and saying, is that the best thing to do? Or could you take things that are already existing in the market and do some really good research to understand them better and apply your knowledge and your expertise in that way? So just, do we always need to be finding new isolates? Because from a commercial point of view, a new isolate has got to be something like 50 to 100% better than the existing isolate to even start to look or justify its commercial development, because it's so expensive to develop something. You're not, a commercial company is not going to invest in new strain or isolate unless it's significantly better than something they already have. And then the commercial companies will move on to the laboratory screen. And also the part that researchers miss out is registration. So commercial companies think right at the beginning about registration. And what this often is safety, is thinking, am I working on something that is going to be a problem? So first thing, if you're a microorganism, you really want to make sure it's not something that's human pathogen. You've got to have that up front because you don't want to cause harm to yourself in the laboratory, but there's no way it'll get into the market if it does have any problems with that. So it's bringing those ideas about safety and about registrability of something right to the beginning. No, I don't want to propose that you inhibit innovation and some great ideas you have at all, but I think it's always good to have in mind saying, is this something that can be registered? Is this something that I can get into the hands of the farmers? And then some of the early questions that a company might have is, you know, can this microorganism be produced easily? Or if it's a botanical extract, is there ways in which we can get it? Now, you might not need to research all those elements, but you need to have a picture of like, okay, I think, so I've got a Bovaria. I know that Bovaria bassiana are available commercially. That means that it probably can be produced easily. But if you're working with a species which is relatively new, can it be produced? Because if you can't produce it, it doesn't matter how brilliant it is at killing something, but if you can't produce it, it's never going to get into the marketplace. It's an obvious thing to say, I know, but sometimes as researchers, we're so excited about what we've found that we forget to think about that. And then what a company will do is, it's a reverse question. So the first question we tend to ask ourselves as researchers, and as we're encouraged to do when we do PhDs or masters, is how does something work? And I was just going to challenge today for you to reflect upon, but is a better first question is, does it work? Because if it doesn't work, it doesn't matter what it does or how it works or anything, but if it doesn't work, it'll never get to the farmer. So maybe the first question you should be asking is, does this work? And then the second question is, how does it work? And that's very different, in my experience, to how most researchers think. And it just, you have to sort of work that through. But that's what a commercial company does. The first question they'll ask is does it work? And then a commercial company will go on to sort of move into they move out of the laboratory as quickly as possible, because for me, a laboratory screen just says something works yes or no. It doesn't tell you much more than that, because these substances have multiple modes of action, and a laboratory screen is too narrow. It only tests perhaps certain modes of action. So for me, it's really important to have the emphasis on this point 6, which is small plot tests, is you get onto a plant as quickly as possible. And then the art is how to run those small plot tests in a way that you can do them fast, inexpensively. They don't take too long to do. And there's some smart ways that you can do that. And that's sort of what I'm going to talk about a little bit about how the smart ways in which we can do that. And that you, instead of using the laboratory screen to do all your work, you move quickly onto a small plot test, and that you're looking at what happens when that substance is on the plant. Do I stimulate plant defense mechanisms? All these other multiple modes of action, how do they come in terms of, you may not understand them all, but the first question you're saying is, does it work in this situation? Okay.
Just Roma, just to interrupt you, you've got a couple of questions. Might be good to, yeah. And that's really interesting. I really like the steps there. And I'd be really interested from those in the room, particularly those that are experienced researchers as well, just whether you do all these points as well and think about these things around the registration, but also thinking up front, I guess, around its use, for example, and whether it will be effective. Here's a question here from Lorena. What is the average number of biocontrol candidates or isolates screened before identification or selection? How to find these new isolates?
So what's the average number screened? Oh, yeah. Well, there's no hard and fast rule for that. It depends. There's different. Some companies have got massive screening programs. They've got really big gene banks or culture collections of microorganisms, and they're screening hundreds and thousands. But I've also seen other people who are more targeted in their thinking, who have sort of worked through a lot of the questions before they start the experimental work, and been very targeted in what they're going out saying, okay, I know I want to kill this insect. So what they've done is maybe gone out to the field and found that insect infected naturally with the microorganism, and then they're working on fewer strains. So you've got a real cross section, and what you have to do as a researcher is sit and think, for what is the problem I'm trying to solve? So what's the market? And for that market, you sort of think, okay, it's this insect or this disease, and then you sit and puzzle through and think, okay, for that insect and disease, what's already known about what's out there that I could use? And then you sort of slowly work through and say, okay, that's what's already known. How should I find something that can work against it? Plus, you always have serendipity. You come across things, and as a good scientist, what you're doing, you're observing when you see something, think, hang on, that's kind of interesting, and you pick up that way. So there's not hard and fast rule to it. It depends on what you're trying to find and what your target is.
Yeah. Here's another question then. How much time can steps 1 to 4 take?
Good one. That depends sometimes on how much money, but 1 to 4 on that slide, I think you can do that in 1 to 3 months.
Okay.
1 to 6 months. That's what I'm saying. That bit should go really fast. And the laboratory screen, people design laboratory screens which are really complex. Really, the main value of a laboratory screen is saying, do I have activity or don't I have activity? And I see a lot of researchers spend a lot of time getting a laboratory screen to refine it, and they're asking questions about how something works before they're asking the question, does it work? So what I'd encourage people to do is perhaps think rationally about what is the question they're asking in that laboratory screen. What are they trying to find out? And really refine that down and try and be very targeted about the experiments that you do.
Yeah. Here's a two other questions. I had this question a little bit too around sort of this focus within universities. You do have a very close link to your professor or whoever your guidance person is. And often Pierre's just making the point here that the focus of the teachers or professors are not commercial products in general, but rather the sort of research process, I guess. So how do you sort of maybe bring in more of that thinking, I guess, or where do you need to change it, or do you think you need to change it more and bring in more of a focus around farmer needs it, or is there a bit of a balance there around pure research? What are your thoughts on that?
No, those are really good questions. Yeah, because I did some there's no doubt about it that I'm really driven to find solutions for farmers. So I've got to say that's what I think. But that's not to say that I'm in any way saying there's a lot of value in doing some good quality pure research. And when somebody starts in a master's or PhD, part of that process is learning how to do research. So it's to some extent doesn't matter what you're working with. But I kind of take the view and say, what if actually we all worked on things that were going to be useful for farmers? We still can do good quality research. We can still ask really good questions and find out a lot of good information. But there's a possibility also that we're working on something that is useful for farmers to use. And so I did some research a few years ago to sort of think, well, where are the problems what happens in that process? And I sat at lots of meetings and I hear researchers saying, oh, I went out and found a new isolate. And I think, oh, well, why did you do that? There's a good commercial isolates available and we need to know much more about some of those. So why did you go out and find something new? Why didn't you take something that was already available, collaborate with the company who's developed that, and ask some really good fundamental research questions, which would still get you a PhD, really good quality work, but you're working with something that will end up, improving the situation for the farmers. And then what I slowly came to realize was actually some of the situation was to do with the questions that the professors were asking. And I don't mean to unduly critical to the professors, because the professors are helping the students to get a master's, get a PhD. But oftentimes they do this, go and find a new isolate and screen a new isolate, because it just generates a lot of data. It helps you develop your master's, it helps you develop your PhD. And so it's a sort of a feature of the research system. But I would really encourage professors to say, do you need to do that? Could you actually sort of take an existing technology and actually really start to understand more about the mode of action and biology and ecology of something that's already available, and it adds to the knowledge and helps the farmers.
Yeah, excellent. No, good words. Okay, thanks, Roma. You've got a few other questions, but we might come back to those because I think they might be a bit more relevant in the next section.
Okay, so we looked at this production process and what you thinking about. I'm talking about research and development. So what you think is, I'm going to start saying, well, okay, let's think about active substance acquisition and about screening. I'm not going to do that, partly because of some of the questions that have come back. But I think if we're looking at developing something that is for the farmers, then the first question we should be asking is, what do the farmers need? So I'm going to turn this back to front, and I'm going to say, why don't we start at the end? So what I'm going to say is, what happens if you start to work on that research project and you're thinking, I want to develop something that farmers can use? So the end point of all that research is you develop a product label that tells the farmer how to use that technology. What happens if we start there and sort of saying, what is it? What's the problem the farmer has, and what's the solution they need? And that's what I mean by looking at the product label. Sort of doesn't matter what the name of the product or its registration or formulation is called. But if we look at a label, it's like a label is the condensed version of a whole lot of research. You can spend 5-10 years developing something, and it all comes down to the information that sits on the label for the farmer to use. So if you see what kind of formulation you've got, just those small words like wettable powder or emulsifiable concentrate or granule GR, that can represent 2-3 years worth of research to find a really good formulation. And then we say the active substance, it's strain Boveri bassianus, strain whatever, and it contains whatever percentage. The amount of research that's needed to develop that is, again, it's what, 2, 5, 10 years worth of research just to get to that point. So by looking at the label and starting with this and asking ourselves these really hard questions, we start to direct our research as well. So what's the product intended for? What's the crops I want to use it against? Do I want it used in protected situations, in field situations? What crop growth strategies are going to work best against? If one of the attributes is that it stimulates plant growth, does it do that on young plants? Does it do it on plants? When should I use it? And how do I use it? How many times should I use it? And then yes, you have questions about pouring and rinsing, because those are safety questions. So that comes back to me saying, is it safe to use? How do you use it? How do you prepare it? How do you mix it? But what's also useful for the farmer to know, and this is where I come to in saying you can take an existing isolate, and there's a lot you can learn to know about it, is what happens, how does that microorganism survive? What's the effective temperature? How does this microorganism work in an integrated pest management system? What happens when I put that onto the crop? What's the interaction with the crop? What's the interaction with the crop microbiome? What's the interaction with the insect as my target, or the plant disease as my target? What are the unintended side effects? So trying to find out whether an isolate has an effect against, say, a beneficial arthropod or a bumblebee means you have to understand an awful lot about the mode of action. So for me, if you start with a label, it's a way of distilling down all those many, many thoughts you have at the beginning of a project, and to sort of focus them and say, you can't, in your a research project, you can't answer all those questions, but which of those questions do I want to answer? Which are the most interesting to answer? And which are the most important to answer? And it sort of engenders a way of thinking. So one of the things about biopesticides or bioprotectants is, do they work? And I know from the previous work that sessions that we've been running, this is a really important question. People are saying, does it work? So I'd just kind of like to get a sense from you all, and to run this poll and see if everyone's still listening. Is, what do you think when you're researchers, you're working on something? What's your target? How well do you think the botanical or the microorganism should work? So if you can sort of start to answer the questions in this poll about what level of efficacy should you get in trials? What level of efficacy do you think farmers want from those products? Because if you don't know what level of efficacy, how do you know when an isolate you're working on, or whether botanical you're working, good or bad? How do you make that decision? So what is the effect you're trying to obtain? And this comes down to the question is, does it work? And then the last question is you then want to get through registration. So what will the regulators expect? So if you can take a few moments now to start to fill out the poll, and be really great if as many of you who as possible can answer this.
Great. And Roma, while people are just filling that out, you've got a few questions in the chat.
Okay.
So maybe if you open up the chat, you could maybe select a few. There's actually quite the small plot tests. I think we're going to come back to the trials, but I see there's 3 at the end, and there's one a bit further up too as well.
So what last one I can see is can you throw some light on how to tackle the attenuation of microbial active ingredient in biopesticide development? So so one is, there's a big assumption that you get attenuation. So I think the first question I'd ask is do you have attenuation? So some strains are very stable, and that doesn't happen, and some strains it's not. So I think that's the question to ask, is saying, is my strain prone to attenuate? And what this means for the non-microbiologists is does my strain change? Will it become less pathogenic, for example? So one of the ways I think to manage that is you look after your isolates very carefully. And one of the key ways commercially that's done is you, instead of serially culturing a microorganism on plates or on media, you periodically put it back through the host to make sure that it remains pathogenic. So you do 2 things. One, you look after the strains really well, you get them into the freezer, so you've got your original isolate, because all sorts of things can go wrong in the lab, and someone mixes them up, mislabels something, something gets dropped or lost. So you always, as soon as you've got something, you make culture plates, and you get some of that microorganism into a freezer or low temperature storage to look after it, or the right conditions. So that then you manage that you don't have serial subcultures, and you're careful about how many subcultures, and you track that. So when I was doing research, I always used to put an extra name at the end to indicate how many times I'd subcultured something. So if I was sort of marking my plate and I had that Biopesticides strain XX1, and that means it's had one subculture, then 2 for second subculture. So you track that, and you're really aware of what you've done, and then you periodically will put it passage up and check that it's still pathogenic. So that's sort of good practice for microorganisms. Somebody's asked me a question about blastospores, really specific questions I'm getting on this, in liquid substrate rather than conidia. So this is about, so the question from Pierre Sylvie is to say, some researchers are working on fungi and entomopathogenic fungi. I think this is a question about, and fungi form conidia, and mostly when you're working and storing and developing something commercially, you're developing conidia, and that's because conidia are really stable. They're this life stage that persists in the environment. So this is a life stage that we know is good for commercially. But fungi also produce something called a blastospore. Now, the blastospores are, their survivability is less good, and so this is why we don't see them commercially. But what we can see is there's a lot of good commercial development coming along, which is able to look after those blastospores better. So you're able to downstream process them better, preserve them better. And because you can preserve them better, it becomes feasible to think about using blastospores. And usually there's not a difference in the efficacy between a blastospore or conidia, but that's certainly something I would look at if I was thinking of going down the blastospore route. So I think we've got a question then, is what tests are needed to identify the active substances in a microbial pesticide? So if this is to identify it from microorganisms from a taxonomic point of view, then you'll do that you could use classical microbial techniques, but more often now genetic techniques are used, where you'll find published papers on the strain, and you look at those published papers on the strain and look at the techniques they use to identify the type of strain, and then you either yourself or you share your culture with a lab who has the capability to identify that your strain and say, how does it compare to all the other strains, and build a phylogenetic tree. So how are we doing on the poll then, Alison?
Excellent. I'll just put the answers up there for you, Roma, and thanks for giving such solid responses there to some very specific questions, but also a range of very, very good questions. So thanks everyone for putting those up, and keep them coming.
Okay, so really interesting answers. So the majority of people think, so if we think, I'll do my maths very quickly, just over 50% of you think you should have 75% efficacy in a trial. Some of you thinking, well, 50% is kind of okay, and some of you thinking 25% is okay. I'm not going to tell you what I think, but hopefully at the end you'll find out. Okay, so what do we think is farmers feel is acceptable? So again, this time, well over 60%, nearly 70% of you think the farmers are looking for 75%. And I think that's a good reflection of the current situation with farmers, because they're really used to working with crop protection agents, which they're told give that level of efficacy. So the expectation is that's what they need. And I think if we think as biologists and ecologists, we really question, do we need that? Because what we're trying to do is we're trying to reduce the pest population to below a damage threshold. And sometimes you don't need to kill 75% or above. And what I know and have come to realize is that most microorganisms, many botanicals, cannot achieve that, and they're never going to achieve that. It doesn't matter what we do or how good they are, they won't do that, because it's a biological function of the environment they're sitting in. You know, you put a microorganism into the natural environment, and it's having to compete with not just against the pathogen that it's trying to attack. There's other microorganisms out there. There's the wind and the weather is affecting it. So we won't get high levels of effect. And what we need to explore is say, if my strain can only ever kill 60% or 50%, how do I use it in a way to give the farmer a high level of effect? And that's also about my earlier questions of saying, it's not about finding sort of a perfect strain, because I can make any strain kill 100% in the lab, because I can change dose, all sorts of things. That's not what happens in the field, and we need to, that's why I say let's get onto those plants as soon as possible and understand what happens, and really explore why we think we need a high level of effect. Farmers actually want consistency rather than a high level of effect. So yeah, really interesting, and I just would like to challenge back to all of you is to really think through why you have to have a really high level of effect, and saying, is that true, or is that, why do we think that? Thanks, Alison. Okay, so I can see there's lots of questions, but I think I'll move on in the presentation, and we're going to have plenty of time at the end for questions, and I'd encourage you to bring those up then. So that was really interesting poll. So hopefully we can explore a little bit about what I'm saying, because I know some of you think I'm crazy when I say, oh, you don't want a high level of effect. And some of that reasoning about the level of effect that we want is to say, what is efficacy? What do we mean by is something effective? Do we mean how much is it killing? What do we actually mean? Do we want to know how it works within an IPM? What is the impact of the interactions of chemical pesticides? What is the effect that we're looking for? What diseases do it affect? What are the disadvantages? What are the advantages? So when we talk about efficacy and we talk about how well something works, I'd encourage you as researchers to think through what we mean by that, and what's the questions that we're actually asking. And of all those questions we're asking, which is the most important questions that we're asking? And what is it, again, if you say took a strain that was already available and you're looking at it, what is it you want to know? And what is it, how do we understand what is it that changes how well something works? And understanding those parameters that explain the situation when something works well and doesn't work well is really important to the farmer, because you can give them really good advice then about how to use that product. So picking up again on the level of effect that we can have, here's some products that are approved in Europe. And if we think about that 75% or 80%, we can see that there's products approved which aren't hitting that target. And yet they're in the marketplace and farmers are using them widely and their acceptability. So this idea that we have to have a high level of effect is not necessarily always true. As I said, farmers want consistency, and then they need support and encouragement of how to use the products to get the best out of them. And the only way they can do that is if we understand the mode of action and how something works well. Because this graph, I'm modeling two things. So if we look at the light green line, what that's modeling is somebody's monitoring their population really well. They can see the population is beginning to increase. They come in with an intervention and they sit on top of the population. They stop it getting to a high level. Now, what actually happens often is, what's the blue line, is we've not been monitoring well, or you had weather conditions where the pest or the disease has really taken off and you've gone above your damage threshold and you've got a problem. Farmer wants to come in. So what you do in that situation is make an application of your product. So this line is modeling if I actually only had round about a 50% effect, and I've assumed that between applications, you've got a 20 to 30% rebuild of the population. And it becomes really, really simple. But if you have a 50% effect twice, you're kind of getting to having 100%. And it's as simple as that. And it then comes to an argument saying, well, if I only will knock out 50% of the population, I knock out 50% of the population now, and then I want to knock out 50% of the population. What information do I need to know when I make my next application. And that's why I'm saying there's some really interesting science to go on and saying, what is that understanding how fast the population is growing of my target? Is it understanding how long it takes my active substance to work? Is it understanding that my active substance only works against the young stages, for example? So there's no point putting it out when they've only got large larvae present. So this is what I'm saying. There's a lot of really lovely science of understanding what the products can do and how it interacts with the targets. And the idea of just getting something, spraying it out there and hoping it works is not the really, really interesting biology. The really interesting science is understanding all the details of these interactions. So I just really encourage you to think again about this idea that you need to have that 75% effort and above efficacy, that you can have lower than that, but you need to understand when you've got lower and how do you manage that. And then we start to do trials. So I see a lot of research that's done and a lot of research papers written, and somebody has done one field trial and they've made a massive amount of interpretation from this one field trial. So I'll tell you now, when I'm working on developing a product, I have done, for some of the products that have been developed, I've done 300 trials, and I look at the data from the 300 trials and I still have questions about what's going on. So I really sort of saying, is the best use of somebody's time to go to a large scale field trial, or is the best use of the time and resources to do a series of really good quality smaller experiments where you're asking some really good questions and you can manage the conditions? Both answers could be yes to both of those could be the right answer, but you have to understand and think through again as to which is the right answer and why, and really think about that and lay out those thoughts before you jump in and start doing some work. And I know a lot of the trials fail. You have a lot of trials, and that's, you know, when I started, it's because I wasn't very good at doing trials. I didn't really understand my insect well, or I didn't understand my disease well, and I didn't understand my botanical or my microorganism well. And so it started me thinking and saying, okay, how can I do this better? Because as a researcher, you've got a limited amount of time, limited amount of money. And I realized that I needed to go back to the drawing board and I needed to do a lot of thinking before I even got to actually doing an experiment. And what I'm going to share now is some of my thinking about where I got to in doing that. So the first thing I started to think about was, okay, what's the relationship between the amount of my microorganism or botanical I put out there and my host? And I suddenly realized I had no idea about that. I didn't know what the relationship was. So if we look at this graph and look at the gray line, which is a chemical, so there's a lot of information out there that the majority of conventional chemical pesticides have a sigmoidal dose response curve. And there's a lot of what we do is based on the assumption that we'll have a sigmoidal dose response curve. And that's not true. If we look at the light blue line, this is what happens with a semio-chemical. So for a semio-chemical to work, the insect, and it's usually an insect, doesn't detect the semio-chemical until it gets to a threshold. And then the semio-chemical has all of its effect. And if you increase the amount of semio-chemical that's out there, it increases in the length of time that semio-chemical is around and has its effect, but it doesn't increase the effect that it's having. And this is sometimes something that we need to really think through. Then I think for a botanical or microorganism, what I've put sort of the green line and then the darker blue line there to represent what might be happening. But each of those microorganisms you're working with and each of those botanicals, it will be different. And I think this is a question to start to ask yourself is, do I know enough of that dose response curve? Because if I don't know that, how do I make a decision about what dose I should use? And what I've also come to learn is that I rarely see a consistent dose response curve for a microorganism. I see a dose response curve sometimes, but I don't see it consistently. And that's because I haven't got enough research time to find out what's influencing that dose response curve. And this comes back to me again saying that maybe taking an existing isolate and really understanding what's influencing that dose response curve is the interesting piece of research. But unless you understand that foundation, I think it's very hard to go on to understand how do you thinking that label that we're talking about, how do you recommend to the farmer how much to use if you don't know what the effective dose is? So one of the things that I think has a big influence on dose is the pest population, the target population. So again, something I often hear people saying is biocontrol agents don't work when I have a high population number. And so I just sat and thought about that, and I thought, is that true or isn't it true? And I realized I'm thinking, oh, I don't know. So I had the data from about 300 trials. So it's the same microorganism strain, and it was tested against different insects, but this is the data for just one insect. And what I did was I plotted the level of efficacy that I obtained in the trials, and these are commercial trials run to GLP. I plotted the level of efficacy I got against the size of the pest population. And this is what I ended up with, which I think is pretty much looks like a map of the stars in the sky. And I was thinking, oh, I might get some correlation in here. And if you were looking at sort of saying, okay, do I have 50% efficacy? You would look at that and say, okay, if I'm looking for 50% efficacy, more than 50% of those 300 trials have failed because I didn't get to 50% efficacy. Now I looked at it in a different way and saying, no, it didn't fail. That trial is telling me something about the way in which this product works. What it is I didn't understand what it was telling me, and I needed to spend some time thinking about what it's telling me. And what you can't see it on this graph, but what I went on to explore and understand was that the way in which that particular product was working was related to not the size of the population, because I could have a high population and good efficacy, and I could have a low population and bad efficacy. So what I came to understand was what influenced the way in which the product worked was the rate of population growth of my target pest. So because I was dealing with a microorganism that took time to germinate and to kill, if the pest population is growing rapidly, the control agent didn't have enough time to work fast enough to stay on top of the target population. And I think this is probably the bigger influence, is not the size of the population, but the rate of population growth. So then in terms of research, this opens up a really interesting area of research to understand the interaction between the biocontrol agent, whether it's botanical or microbial, and the rate at which the population's growing. And sometimes we don't understand that well enough. And I certainly understood that I hadn't understood that well enough to really understand how to make the product work. And then looking at the 80%, look at how many trials we might have considered had failed if we were trying to say that we wanted something to be 80% effective. And then the other thing I came to discover, I said at the beginning that, how well something works is different. And as a researcher, let's not interpret too much from one trial. So if we look at this set of trial data, so I ran 5 trials, and in this case, it was a microorganism, and I was trying to control a common disease. So I ran the 5 trials. Now, if we look at this trial, this is absolutely perfect. So if we look at the green bars, as the green bars get darker, the amount of product I've used increases. So that's great. So what I can see is the more product I use, the better efficacy I have. So I have a lower amount of disease. But I also got this, where in fact I got the best for the lowest rate that I used, and then I got everything in between. And when you look at the mean, you can see actually there is some indication that the higher rate worked at 4 litres per hectare, but that was twice as much as the 2 litre per hectare, which can be twice as expensive. What I should also tell you about these trials, that these trials were done on the same crop at the same time with the same researcher, with the same equipment and the same product source. So everything was kept the same. The only difference was there were different sites. And that's the variation I got. And so I was trying to understand how I could do my trials better. And what I came to realize is this variation is perhaps the natural variation we see. And we can't change that natural variation, but we can understand it. And then by understanding it, we work out how to work with it. And before then, I just had a tendency tendency to think, oh, I need to get rid of the variation. And I now sort of understand and saying, no, this variation, this variance is part of the system. So why do I say that? What do I mean? So if we look at this sort of models of the effect in a trial, so what I've modeled on the black line is a chemical, and most chemicals have a variance of around about 3-5%. Some are a little bit higher, but that's a good average. And we're looking at a microorganism or a botanical on the green line, and we're looking at, say, a variance of sitting round about sort of 10-15%. But then I looked at my trial data and sort of said, actually, I've got much higher variance than that. I've got 30 to 40% variance. So when I run a trial, I'm going to have a data scatter that ranges from 80% all the way down to 20%. And that's what that previous star chart I showed you, that's what we're seeing. And again, this is the variance that's naturally there. And what I start to have to do is change my thinking and think about, how do I manage that? How do I work with that? And how do I understand what's influencing that? Because as a researcher, unless I understand what's influencing it, I can't understand it. I can't advise farmers. And taking the same idea, so let's assume we've got a sigmoidal dose response curve. What's really interesting here is if we look at this, so you think, okay, so the better something works, so sitting at the top of this bar, the wider the data scatter. It's just a numerical value. So when something doesn't work well, I have a narrower data scatter than when something works well. So if we've got something that's working up at 70%, I will be seeing data in my trials that ranges from the 90, 100%, but all the way down to the 40. But on average, I'm going to get 70%. And this is not what we think is going to happen. And as researchers, again, and doing experiments, we need to think about that and think, okay, so oftentimes you look at your data and think, oh, it hasn't worked, something's gone really wrong. But it's not, it's just a function. If you have a 30 to 40% variance, you will have a wider data scatter, the higher, the better the product works. Once you get to 100, it's capped, because you can only have variance below 100, you can't have variance above that. But below that, this is the kind of things that you see. So yeah, this is just me focusing down in to say that this is the data scatter you get. Sometimes the better a product works, and it's really hard to work on this. So instead of trying to say, I mean, of course we should do really good experiments, of course we should manage this as much as we can, but there's also an element to say, this is what these systems do. What I need to understand is what influences the systems, and then how can I work with them? And this is, again, why I think there's so much interesting work we can do, working with existing isolates rather than doing something new. So I worked with a statistician on this work, and what I discovered, because I'm not the world's best statistician, so I liaised with an expert on this, and I actually worked with a statistician who was an ecologist, and so different group of different type of stats. And what he taught me was that the biopesticides multiply the variance in the system. So you have the variance due to the plant, you have the variance due to your disease or your insect, and then you put in the biopesticide. And instead of that being additive, it actually multiplies. And this is why we have this explosion in data and this vast variance. So we're trying to do experiments with something which has a variance of 30, 40, 50%, and it will always have that variance. But what we can do is understand a little bit about that variance and about how it influences it. And this is our challenge as researchers. So if we have that variance, we accept that that's there, what can we do to change it? So when we start to do experiments, or when we're starting to do any sort of research on efficacy, we have to think about all of these different things. We have to think about the agroecology, how's that plant grown, what's on that plant, how it's interacting, what's that variety, what can that variety do, how does it respond, what's the disease or pest inoculum, how much is there, and how much I can manage it. We have to think really carefully about how we design and analyze our trials, and maybe we should start to think about better trial designs, about better approaches, because we're starting to think not in the way that we would for a conventional chemical pesticide, but we're thinking about this as biologists and ecologists and understanding the system that we're working in. We can think about the treatment regime that we're putting on. Why are we doing a dose response, different doses? What do we expect to get from that? Have we chosen the right doses? We think about how we place the biocontrol agent into the crop, and we also need to think about how we assess how it works, how and think about all the other factors that are going on in the system. So what I also know is what we find in the lab to the field, and we all know this, is that the results we get in the lab don't transfer to the field. It's very poor. So then I ask the question is, why do we keep working in the lab if we know that? So this is why I advocated at the beginning, say, let's get onto the plants as soon as possible. And let's really start to understand what's happening in the system. It's more complicated. It's much harder to do, but that's what we should think about. When we put a reference treatment in a trial, for me, the reference treatment is just to prove my protocol worked. I'm not trying to say it worked as well as against the reference treatment, but maybe sometimes that's a question that you're asking. I raised at the beginning that how do you find out what the dose response curve is? Maybe we need to do some really good work to understand that. And then I've talked about variance, is maybe just take some time to understand what is the variance that I have with this botanical or microorganism that I'm working with, and what experiments can I do and design to understand that. Because if I understand that my variance sits at 50%, it helps me interpret my trials better and helps me to understand it. And thinking also that the effect of the biocontrol may not be in days. So am I assessing it at the right time? How do I design an experiment that considers that? Thinking about why am I putting on 2 applications? What am I trying to do by putting on 2 applications? And how do those applications interact with the life cycle of the pest? How am I applying it? Does it end up on the crop? What am I trying to do? And then sometimes if you're working in the field, you can't go into the field because you've got crop destruct, it's too expensive. So you have to think like Semio-chemicals. How on earth do you do trials when your plot size has to be about 3 or 5 hectares? So the way I sort of what I've learned and how I try and tackle this is I try and think through what I know about the mode of action. I try and think through what I know about the dose response curve. I try and think through how that biocontrol agent might be working in the agro system on the crop I'm putting into it. I'm trying to think through, am I asking questions about how this substance would work in an integrated pest management program? What other interactions am I kind of looking for? What am I looking about in crop survival? What's the effect of adjuvants or application? And each one of these is kind of almost a PhD in its own right. But I think there's a lot we can do by just starting to think through these aspects and then trying to work out which we think is the most influential aspect and how do I account for that, and how do I understand that, and what research do I do before I move into the field. So I'm going to move on a little bit and talk about some of the more detailed about the sort of designs that you could use and how you can, to help you sort of think through and design experiments. But I want to take a pause and see whether any questions have come up.
Great, lots of comments. Thanks, Roma. It's incredibly interesting. And what I'd quite like people to do is you'll see a reactions button at the bottom. And if you could go to that, press it on, and then maybe give us a thumbs up if you have done field trials. And it's a bit hard with COVID, I know, because things have changed. But have you done field trials in the last year, or are you thinking of doing field trials in the next year coming? That might give people a little bit more scope, since we're hopefully, look, there's lots of thumbs up there.
To work in the fields.
Yeah, I think everyone wants to get out of the laboratory. Well, even in the laboratory has been a challenge, but getting out there in the field is probably pretty popular at the moment. But look, there's lots of thumbs up there, so that's excellent to see.
Could I ask a second question?
Yeah, go for it.
Yeah, so what would be really great is if you'll get your thumbs ready again, is to say to me, how many people have had trials that failed? Have put your thumb up if you've had trials that failed. I've definitely had lots of trials that failed. Yeah. So hopefully some of the things I'm saying will help you to have less trials that failed, and you can sort of learn from the mistakes that I've made to see if we can have less things failing, because it's so frustrating. It takes a lot of time and effort to set up a trial. But one of the things I definitely learned is I was too keen to get to the field, and I didn't spend enough time thinking about what it was I was really trying to investigate, thinking about what the question I was really asking, and then designing my experiment really well to answer that question. And what I was really lucky. I worked with somebody who made me go and talk to a statistician, and I worked with a statistician to co-design my experiments. And that was probably one of the smartest things that I did, because by working with the statistician, and because I went to him and I said, this is the variance I have. I don't know what my dose response curve is. How do I design my experiment? And he helped me to work together to design really good experiments. And some of that is in the part I'm going to talk about next. So I really sort of think as ecologists, perhaps, and think about stats related to ecology.
Great. And you've got some comments here too, Roma. I mean, there's one here from Alex, and saying that we can see the population growth, like Roma already mentioned, on our trials as well. So great to hear you're doing trials. And just emphasizing here that the understanding your product, pest biology, and application on the correct timing is the most effective and also cheap way to control pest. As at the moment, we're doing trials against fall armyworm in Africa and Asia with maltodextrin, and results are great. An important factor that we have identified and is crucial for effective trials is the difference in climatic conditions and the timing of pest pressure. So great to hear those comments. And we've got some others that are doing field trials as well. So please tell us if you are. There's a comment here by Pierre, and I think this is quite interesting. It's just that, are researchers actually able to do more than 3, 5, 10 experiments per year in their country at field level with one biocontrol product? And I guess that's it's actually interesting. What is the reality?
Yeah, I think that's a really good question. That's sort of what I was alluding to, is saying, you've got 3-5 years worth of funding, research, and you've got to do trials. And that's what I was trying to say, is the best use of your time and effort to do extensive field trials or really well thought out smaller plot trial work.
Yep.
And that instead of rushing to the field and lots of things that potentially could go wrong, etc., is just taking a little bit of extra time to sit and think about what it is the question you're asking, thinking about how to design an experiment. And being really talking to other people to gain knowledge. So one of the things I used to do was go and find somebody who knew everything about the insect or the disease I was working on. And I just used to pick their brains to tell me everything they knew about the population dynamics and all of that information, which meant that I didn't have to research that. But it meant that I then had the sort of key information to think, okay, if I know that that's what the population does, that its life cycle, that it goes from egg to adult in 5 days, and it's only the larvae that's susceptible, you think, okay, I'm going to have to start to get something that works really quickly. But equally, how synchronous is the life cycle? And it's gathering as much information from the literature, from other sources, and just sitting with a piece of paper before I even went to the field is a way to save
Sounds
time.
good, Roma. It sounds actually pretty sensible for most things in life, sitting down, thinking a little bit first and being targeted and efficient. And look, I guess you're going to tell us next about some of these, how to do some of these trials in kind of a bit more of an efficient way, and maybe something that's a little bit more practical too, and faster to implement. So go for it.
Hopefully you can learn from some of the mistakes that I made, and then you don't have to make them, and it allows you to move forward faster. So so this is just sort of perhaps at the later stage when you've past discovery, then you're going to start to be asking questions about the types of formulation, the specificity, target, mode of action. So I just want you to I wanted to pick up just to have that as a consideration. So then we go on to the trial design. Like I said, I worked with some statisticians to sort of guide me and get my thinking. When I say trials, I don't necessarily mean big, extensive field trials. I mean that I was working in small plot trials. So I might have worked mini plots, sort of meter by meter kind of plots, because then I could get more plots in, and then I could ask sort of more questions. Although I always advocate that each trial you try to ask just 1 or 2 questions. Don't make it too complicated. So what I know is that the best trials were to only have 5 or 6 treatments. I repeatedly see work done where I see 12 treatments or whatever. What happens with that when you've got really noisy data with a high variance is that at the end of the trial, you've got such a high level of variance and such noisy data, you can't see the effects that you're having. So what I'd say, well, if you do lots of trials without managing this and without thinking this through, you end up with not greater resolution in your data. You just end with lots of trials with very noisy data. So you're trying to sort of have fewer trials with less noisy data. So I advocate really try and minimize the number of treatments you're using. And the only way to do that is then you're asking much simpler questions. So in a trial like this, I'm trying to really understand what happens, how influential is dose in this one. And so if you can see that I'm using quite a wide dose range. So if I was working with a microorganism, I would have at least 1 log difference between these rates. To have less than log difference, you will never see the effect of that. So the controls in there to see if no effect, what would happen if I did nothing. A standard is in there to say, did I have a good trial design? Did I get the effect I wanted? Lower doses to see what would could I use less product? Have I got the rate right, especially in the early stages where you're not quite sure. The 1N is okay. I've got it right. My experiments, I'm more or less using the right dose. And then 2N say, actually, is there any dose? Does it make any difference if I have a higher dose? Will I actually see an improvement? So think about the range that you're using there and the dose that you choose. And for microorganisms, you definitely have to keep it wide because you won't see small differences. I also sort of think about the question I'm ask myself is when am I going to put the application? Is it best that I need it there before the pest arrives, after the pest arrives? And what happens or do I put it in when the population is growing fast? So the answer to that depends on the mode of action and what the substance is, whether I put it in before it arrives or when it arrives. And it also depends on what the disease is. And remembering often the point at which we recognize we've got a problem with our pest or disease, it's actually already there. So we're actually perhaps always coming in a little bit late. So we need to really think through. But we also need to relate that to not what we can just manipulate in our experiment, but what's going to be happening in the real field situation. When would a farmer detect that he had a problem? Would the pest already be there? And are we trying to treat once the pest's there? So just again, some of the questions to ask ourselves and think about. And then think about what we're doing is the frequency of application. Why are we putting in multiple applications? What are we trying to do? And how often do we want to put them in? Because if we put them in every day, it's too expensive. It's never going to work. So that's not really realistic. Do we put everything every 3 days, 7 days, every month? So some of the things I've looked at is doing experiments where I understand my rate of population growth and I reduce the frequency of applications. When the population is growing fast, I have less gap between my applications than when the population is growing slowly. But you have to start to understand your rate of population growth to be able to do that. But I think if you can do this, you start to be asking the right questions. And I've just put this thing is don't add an adjuvant. It makes your trials even more complicated. You put in another variable and you don't necessarily know what the variable is doing. So my really strong advice is keep it as absolutely simple as possible, but really well thought out. I'd rather do a really simple trial asking one question that gives me good results than a complicated trial with lots of questions and I get half an answer that I don't really know about. And then we think about the plot layout. What's the best layout? No, we're all treated, randomized block design is the best design that you can use. And if I'm thinking I've got 5 treatments, now I advocate 6 replicates. And this comes from work I did as a statistician, that working with less replicates is, if you have really high variance, it doesn't moderate your high variance that you might have. Working with more replicates, it sort of increases your chance of having the outliers. So 6 replicates is a nice, good compromise to not increasing my variance too much by having some outliers in there, but I've got enough plots in there. And this comes down to people sort of saying, well, I'll work with 3 replicates or 4 replicates, but I'll do lots of trials. All you end up is lots of trials with the same variance. What you're trying to do is to reduce the variance within that trial, so it allows you to see what the data is telling you. And one of the ways to do that is increase your replicates in the trial. Now, of course, if you increase the replicates, it increases your work. And sometimes if you have too many replicates, it takes too long to assess. You become less accurate in your assessment because it's just so much work to do. So you may think, oh, I'll go do 10 replicates, but really think about how long it's going to take you to assess. And if it takes you all day to assess, you know, is your morning assessment equal to your afternoon's assessment? So you need to think about practically how long it'll take you to assess. And one of the things I know is when somebody's taking a long time to assess, it's a bit boring, a bit frustrating, and I'm definitely not as good at doing it as when I have can assess more quickly. But think about other designs. Think through, instead of just automatically doing a randomized block design, think through, do I need a randomized block design? Could I actually do a completely randomized design, which actually is statistically a little bit stronger? Can I do that design? Why couldn't I do that design when it's not appropriate? So again, just going back to those first principles we were all taught about how we do trial design. And my absolute favorite is working with a Latin square design. Because the statistical resolution that you get working with the Latin square design, and this works really well for mini plot work, this is probably one of the best designs to help you to manage the variance that you've got in there. Now, what you'll see in a Latin square design, because you have to have the same number of treatments as replicates, is I've now got 6 treatments. But what I do for those 6 treatments is I have double controls in there. And that's another way, statistical way, that you can really help yourself, is because by having the double controls, you can understand the variance of your untreated better, and it allows you to get better statistical resolution with your treatments. And that's my favorite design, because it just works so well. But I also, what you have to think about when you're working at the trial design is something I discovered is what happens if my product also stimulates my untreated plots. So we think of a lovely, you know, nice laid out trials in a field. But what happened when I was working with a botanical, and I realized, is that my treated plots, I was switching on the plant signaling, and those plants then sent out the signal and they switched on my untreated plots. So I wasn't getting a difference between my untreated and my treated. So you have to think through a little bit about the mode of action and what might be happening. I solved it in this case by putting a sort of screen between each of my plots. And I could do that because I was in a greenhouse, but sometimes that's not practical. And remembering, for some pests, your trial design isn't going to be a lovely sort of square or rectangle, that you're going to have uneven plot sizes that, you know, if you're working in a forest, they're spread around a forest and you've got odd plot sizes. So again, go back to first principles and really think about the trial design. And that's why I said my target's not evenly distributed. So if you've got, I can remember working in grapes, and some of the grapes had the disease and some didn't. Now, if I put my plot across everything with and without disease, I would have been treating a lot of plants, which I knew would have given a result because it didn't have the disease. So what I did was I spaced my plots out around the disease plants, so that I knew that every plot had disease plants in it. So again, it's just thinking through really carefully, not working on rote, not working on what we're doing, and thinking through and justifying the approach that you're taking. And then how to assess it. We really know how to count dead and live insects. We really need good at counting how much disease I've got, how not. But that doesn't, biocontrols do much more than that. So you need to again think about what it is you're assessing, how you're assessing it. How do you assess this if something's repellent? And one of the things I know working with diseases of biocontrols is that the biocontrols don't stop the disease coming in, so they don't necessarily change your influence, but they do change your severity. So incidence will often look really bad. You think, I've got lots of patches of disease not working. Then you look at your severity and think, hang on, but each of those disease patches is not getting any bigger. And then if you take that crop to harvest, what you then see is saying, what my biocontrol did was it stopped the disease having a profound effect on the physiology of the plant. And look, my yield in my treated plots is actually really good compared to my untreated. So again, it's thinking through and understanding what's the mode of action of your substance, how does it interact with the pest or disease, and how to design your experiment and your assessments to measure that best. And this is just a sort of, I'm nearly at the end here, so I'm just sort of winding up. So this is just an illustration, again, about thinking about things laterally. So So Trichoderma asperellum is something that was developed for treating protected plants in a greenhouse, and to protect the plants against root diseases like Pythiums and Rhizoctonias in the plant. But then somebody else sort of thought, right, okay, I'll take this trichoderma, and I used it to treat the seeds of corn, soy, sunflower, and oilseed rape. And what's really interesting in this situation, yes, it did reduce the disease, but what was most interesting is that it reduced the amount of mycotoxins that had been caused by that disease. And it was able to reduce the amount of mycotoxins to below the levels would. But we only picked that up by going to harvest, by measuring the mycotoxins. So it's just an example of thinking about what it is you're going to assess, and how to assess all the effects that these new substances can give you. So just summarizing up then, when you're thinking about working with these substances, you're thinking about efficacy. It's about population management. It's not about pest kill. Thinking that you're working with a biological system, thinking about the relationship between dose and effect and modes of action. And also sometimes to think about good practice about efficacy is, as scientists, we're trained to find when something works best, but maybe experimentally, it's really interesting, and it's really interesting for a farmer to say when something doesn't work. So maybe it doesn't work when the pest population is growing at this speed, or maybe it doesn't work when the temperature's at this level. And understanding that and investigating that is really useful information. And to not try and think, as we always do as scientists, is we're always trying to find the best, but thinking maybe when it doesn't work, and to consider trial design, think of application, frequency of application, and sit down and work out all of these things before you even get into the field. Thank you. That was where I was going to finish, and I really would like to open up for a discussion now.
Great, thanks, Roma. That was excellent, absolutely excellent, as per normal. And we're going to get some questions coming in. I'm also just going to invite people, if you do want to share something that's happened in the field or something that's really puzzling you in your design of your trials, or actually in your plot testing, or even in the laboratory, feel free to put your hand up, and I can also unmute you, and you can share that with everyone else verbally, or just put it in the chat. We've got some questions coming through, and we've also got a bit of sharing there around I asked Roma if people were working on various things, and also how many replicates they were doing. So Thomas here is saying they're doing 4 replicates, and Pierre was just making an observation that in many countries, in many places, it's only 3 replicates. I think you had 6. That's your ultimate. I
just know that you're working with, I know that working with 3 and 4 replicates doesn't give you resolution data. It's wasted effort to some extent. So working with 3 and 4 really is wasted effort. I'd never worked with less than 6, and I've been doing trials. I'm doing 200 or 300 trials a year. I've been doing it for about 20 odd years, and I just know I cannot get the resolution in the data if I work with less replicates.
Yeah, great insight. Thanks. And here's a question here from Adeline. What will be the design if you have 3 factors, different products, frequencies, and regimes to assess, and you want to see the combination effect?
I would actually split that out into different questions. So I would, I think that's what I was saying, is because of the variance levels we have with biopesticides, it's very hard to investigate those things. So I'd investigate each component on its own, and then take the best result from each of those components on its own and do it in a combination trial. And then, so I haven't got, say, 3 different rates and 3 different targets. I would do one rate against different populations and another rate against different, as 3 separate trials, and to break it down in that way. The problem comes when you ask too many questions in one trial, you just never get the resolution in the data. You've got to separate them out. I know it's more work, but I still think it's better to have done something as a simple trial with a good result than a trial where you never quite get the results you're looking for.
Sounds good advice. For pheromone tests, it's going to be a bit different, the design.
Yeah, absolutely. Yeah, well spotted. I didn't really go into detail about pheromones, and that's because the design for pheromone trials is really quite different. I alluded to the fact that you're working on landscape scale. and that you might not be able to do replicates in the same way, so that you can't have your plots next to each other. You've got to have them a long way apart, so you have to have a different design, and that would be you're actually sort of doing replications in time or across space to be able to do that. So you would perhaps, if you're working in an orchard that's 3 to 5 hectares, you'd have to have another field somewhere else. So what you have to do within that trial is monitor and run it really well. But it's quite reasonable to only have, so that you don't have replicates in the same way, but you have to change how you design the trial and how you monitor it to compensate.
Yeah, excellent. There's a question here just going back a little bit, and it's just around biopesticide application on seeds to control seed-borne pathogen or soil pathogen. Is anything different from that aspect that people should take into account?
Yeah, so it depends what you're trying to do. So some people talk about seed application, and that they're actually doing in-furrow application, so they spray into the furrow as the seeds are closed over. Or some other people are treating the seeds. And I think if you're treating the seeds, we're probably thinking about a microorganism here, you have to think about how you get a good high dose, how you get the dose on the seeds. You have to think about what you're using to get them stuck onto the seeds. And you have to be really careful about what's the survival of the microorganism once you've done that. And I would sort of do some experimental work on understanding that how long they will survive on the seed, because you often see somebody has mixed up the seeds maybe several days before. But yes, maybe you can do that, but you have to keep that in the cold. You have to look at it. So I would do some experiments to see what's the survivability of my microorganism when I do that before I even get to going to the field. So you need to do a little bit of testing first.
Yeah, good point. Here's just a question. JL Tan has been writing lots of great stuff in the chat, but maybe research on biopesticides should not only focus on efficacy on target pests, but also related to plant vigor and plant defense mechanisms, how the product changes the plant defense biochemistry. Yeah. It's complex and difficult to do, but sometimes biological products work and sometimes they don't. And many times we suspect weather, application failure, other problems, but we may not understand the plants well enough. What's your thoughts on that, Roma?
Yeah, absolutely. And I was alluding to that as well, is that we have multiple modes of action, and stimulating plant defense mechanisms is some of the mode of action. And I certainly know that I've done trials with microorganisms or botanicals on wheat. And when I looked at those wheat plants and assessed them, or the trialists assessed them, there was no green leaf area. The disease was rampant. They looked absolutely rubbish. But what I do know is when I went to harvest and harvested it, I actually had a better yield and a better quality from my biocontrolled treated plots than I did from untreated, and in fact from my chemicals. And that was because I had these plant interactions. It was you can't, without a lot of good equipment and a lot of time and effort, it's very hard to assess what's happening in the field as you go. But if that's your question, that's the mode of action question, you can do that. So that's why I was sort of saying, it's in terms of assessment, think about the quality of the yield, and think about the amount of yield that you get, as well as just looking at whether you've killed the insects, etc. So sometimes we can't test all those parameters, because you're absolutely right, it's really complex, but we can test the effect of all those parameters by looking at yield and quality.
Yeah, no, good point. I'm just going to go back to pheromones just briefly, and you sort of alluded to this in your last answer, but around this, but where can we find the design for pheromones? What should be the size of the plots, for example?
Yeah, this has been developed. So I think for a lot of work on efficacy, refer to EPO, so the European Plant Protection Organization. They've got the protocols published, freely available. In there are some guidance documents on how to do trials for microorganisms, how to do design trials well. And they're working on how to do trials for Semio-chemicals. So yeah, keep watching and look there to see when something like that comes up. But one of the things you can do is collaborate, speak to commercial companies who have got pheromones, and they'll often be very generous and share with you trial design and how to do good quality trial design. So, don't be scared to go and speak to commercial organisations who have done a good job, who've got products in the market, because they will have had to come up with good trial design to do that.
Well, that's great advice. I think that's really important, actually. I don't think we do that probably enough. But yes, talking to people already in the industry or in the sector or working in that field, I think is always really valuable. So I'm very much a supporter of that. I'm just going to ask, I think, Barbara, I think you might want to talk. I'm not sure you've got your hand up. I'm just going to ask you to unmute. Let's see if that works. Barbara, did you want to talk? Let me see if it comes up and works. So I don't know if Barbara is there. It may just be, we have this sometimes, it's quite easy to put your hand up and not mean to do it. And it's a bit frightening when someone, oh no, there we go, sorry. I think
Okay.
Barbara means... Hey, there's a really interesting question here. Interesting to think how to design an experiment like the ones you suggested under a participatory approach with farmers.
Mm-hmm. Yeah, and again, I think that goes back to what I'm saying. If you're working with farmers, you really need to distill down what is your most important question and design a very simple experiment, and to get a very simple experiment so that you can then, and I just try and run a simple experiment, but monitor as much and get as much data as I can out of that simple experiment. And that's what I'm working with farmers, is distilling down and saying, what's the most important question we're trying to ask here? So if you've got something where you think that most of its effect is by having plants managing the plant responses, and that in fact most of your effect that you'll have is in the yield and quality, then you have to work really close to the farmers. The farmers will be looking at that plant. My plant that's pretty dead, I don't think this is working. And you just work with them, explain what's going on, and it's about really good communication. But
you're right. I mean, I guess a simple plot design, like, I mean, something that's very simple, that's just testing one thing, that would be a powerful way to actually communicate with and to farmers and show them what's actually happening.
Yeah, really good. Yeah.
Okay, excellent. Next question here is from Adeline. What would be the sample size, or the best sample size, I guess, when testing efficacy on farmers' fields?
So is this, do you mean for, if you can clarify, do you mean for how?
I think it means, so Adeline, you can actually unmute yourself, but I think it's more when you're actually going out to farmers' fields and wanting to test the efficacy of your product on a larger scale.
Yeah, okay.
How do you do that?
Yeah. The size of the sample that you're working with, again, comes down to the target and the crop that you're working on. Obviously, and you've got to be pragmatic and do a balance. You don't want to be still standing in the field when it's getting dark at night trying to assess it. So you've got to think about, how many plants should I assess that are representative of the plot? You know, and if you've got a plot that's 2 meters long, say by a meter wide, and you're assessing in that central area, you're trying to find a balance between the right number of plants to assess to get a good representation what's in that. Again, there's EPO protocols which have some guidance on this, but I think this is where you sort of have to think and talk to a statistician and say to him, you know, how many of those samples do I need? And again, something I used to do was I'd maybe start with 10 samples, and if the data from those 10 samples came in very similar, I'd stop. But if the data from those 10 samples was not similar, I'd then go and do another 10, so I had 20 samples. And you start to understand from your pest combination whether you can be at 10 or whether you need to be at 20.
Okay, excellent. Okay, so Roma, that is the end of our questions for now.
Okay.
I know we've got 2 sessions coming up. Do you want to just tell us, maybe if we go to the next slide, we may have the end slide there, but tell us what you're going to be talking about in part 2, Thursday, 9th of June, in our second part. What are you going to be covering?
Yeah, so I did sort of a little bit back to front here. So I kind of started with efficacy because I suspected most people had lots of questions about efficacy. And hopefully what I've explained today is understanding to be able to run our trials well, to get to that end point of something we can deliver to farmers, we need to understand the mode of action. We need to understand what it is we're working with. And so the next session, I'm sort of going back to the beginning, and instead of asking the question, does my substance work, which is what the trial is, I'm going to start to say, well, how do we look at how my substance works, and do a little bit of exploration around how we can design good laboratory experiments, and how we can design our research programs that we're targeted and we can make good progress. So it's more going to be around about mode of action work.
Excellent, thanks. That sounds exciting, and I'm really looking forward to that. And we'll be sending out a questionnaire to everyone as well, and we're hoping that you will fill it out to provide some valuable information to feed into the next session. I would just like to thank Valent Biosciences and Semio-Chemicals for supporting this series. And I think, Katie, you could probably start your video and just give a wave. People can see you, hopefully, or you may have already started. I haven't got all my my camera on here. Oh, there we go. Right, excellent. Katie's here from the middle of the morning, middle of the night from the US. So thank you for joining us, and I can see some other colleagues in the room as well. Thank you to Putra. Definitely a big thank you to Roma, and a huge thank you to all of you who have attended. I can see there's lots of great feedback in the questions there in the chat, and even some there's another question coming up. Yeah, great to see your reactions there. Thumbs up. We will see you all hopefully at the next session on Thursday the 9th of June. It's been another great session. Roma, really valuable information, and I'm sure everyone learned a lot. Really looking forward to people's feedback as well, and your interaction for series part 2 of the series. So thank you very much, everyone. Safe times ahead, and we will see you back on Thursday the 9th of June. I'm going to stop recording. There's a few more questions, and then if we have time we may just stay on and just answer a few questions for a few more minutes before closing the session. But thank you very much for joining us.
Thank you. Look forward to meeting you next time.